We got a calculator? We're good to go? All right, in this section, we're going to talk about solving exponential equations and also log equations. I know we've solved exponential ones before because that was our last unit, but we're going to see how we can use logarithms today to help us solve exponential equations. Maybe ones that are a little difficult to do by hand. Okay, we can use logs to help us with those. So today we're just going to spend time focusing on the exponential equations, and then tomorrow we'll look at the log equations. We did a little bit with logs on Friday, remember? Like get one log on each side and then use some properties to help you do that. We'll do more of that tomorrow. But let's just first focus on the exponentials. So for this example at the top of the page, if I asked you to get x all by itself, what would you automatically, intuitively think about doing? Subtracting the 3. I like it. All right, so 2 to the 3 minus 2x power, and then if we subtract the 3 over, we'll get 8. That's a really good first step. So let me ask you again, where do you want to go from there? This is when kind of one person might want to do something different than someone else. You have options. What do you feel like doing, Gary?
Turning 8 into 2 to the power of 3.
Okay, we can get the bases to be the same. I saw some other hands up. Does someone have a different idea? Is that what you guys were going to say too? Okay, we're actually going to do this two different ways. So let's do Gary's idea at the bottom here. Gary said turn 8 into 2 to the 3rd. This is what we did in the last unit when we got the bases to be the same for the exponential functions. So now that the bases are 2, where can we go from there? Get rid of the 2's. Okay, we know what's on the left-hand side must be exactly the same as what's on the right. So if the bases are both 2, we know those are matching. Let's go ahead and check the powers. What'd you get? X equals 0. There you go. There's our solution. Okay. Not a surprise to me, at least, that this is what most of you wanted to do because that's what we're used to doing. That's what we did in the last unit. So we're going to go ahead and kind of write down those steps that you took. I know some of us are procedural. You like kind of steps when you reference your notes. So we're going to write down those steps that we did here. We, let's see, we got or get the bases to be the same. After we got them to be the same, we set the powers or exponents equal to each other. And last but not least, we solved for x. All right, that's nothing new. But let me ask you this. What if I were to change this 8 to a 9? Would you be able to solve it the same way? Unfortunately not. Okay? So that procedural, those 3 steps we wrote down, we can't say that's going to work every single time. Okay? So let's think about maybe a different way we can solve this exponential equation. Okay, perhaps using logs. We're going to keep it in 8 for now because at least we know what the answer should be. But just keep in mind, if this was something other than an 8, we would have to use a different method. Okay, so Gary's first thought was to get the 8 to turn into a base of 2. Another way you can think about solving equations is moving numbers or values to the other side, just like you wanted to move the 3 over by subtracting. Now, isn't this a positive 3 on the left-hand side? So to move it over, you'd have to subtract 3, right? You'd have to use an inverse operation. What would you have to do if you wanted to move this exponential base of 2 to the other side? This is when it gets interesting. Would we divide it over? Is this 2 times 3 minus 2x? No, you see how you're not multiplying? Okay, a common misconception with students is they want to divide the 2 over. But this is not 2 times the power, it's 2 raised to the power. So if this is an exponential base of 2, to move it over, it would actually become a log with a base of 2. Have you guys heard me say kind of so far in this unit that exponentials and logs are inverses? They undo each other. Just like if you wanted to move a positive 3 over, you'd have to subtract it. If you want to move a base of 2 over, it would have to become a log with a base of 2. Now, since the 8's already on that side, that would become your argument. And on the left-hand side, we're just left with that power because we moved the base of 2 to the other side. If we were to kind of check our work there, if you were to work backwards, wouldn't you try to think about this as 2 to the power of 3 minus 2x is 8? Remember doing that conversion in the first section? Isn't that exactly what we have here? So whenever you're moving an exponential base to the other side, it has to become a log with that same base. Let's see if we can keep going. What power do you have to raise 2 to get 8? 3. And if we solve for x from there, we get the same answer of 0, which is great. But do you notice I could easily change that 8 to a 9, which would therefore make this log base 2 of 9. We can type that in our calculator if we wanted to, and we would get a new x solution. Okay? This method, by moving a base to the other side and making it a log, is going to work every single time. What we did down here at the bottom only works if we can get the bases to be the same. Do you see how this way is a little bit more restrictive than what this is? Okay? So if you're used to getting the bases the same, that's wonderful, but it has to work out that way. If it doesn't, we're going to utilize logs to help us solve for x. So we're going to get into that kind of practice mode, is whenever we move a base to the other side, it becomes a log. Tomorrow we're going to check out if we move a log, it becomes a base. Okay, they're inverses or they cancel each other out. So for you procedural people, let's go ahead and write those things down. So the first thing we did way back when was we moved the 3 over to the other side, and we were left with this exponential piece, 2 to the 3 minus 2x. We're going to try to do that first. We're going to isolate the exponential, whatever the base to the power is. Anything else we're going to move to the other side. Once we isolate the exponential, we're going to convert it to a log. That means moving the base to the other side. And once we move the base, we can solve for x. We're going to spend the majority of our day doing that first block. Okay, using logs to help us solve exponential equations. What's always our kind of last resort, though? Let's say we can't get the bases to be the same. Let's say that for some reason logs are not going to help us out. If none of that can be done, what else could we try to solve for x? Or how else can we try to solve for x? Yeah? We're going to graph it. Yep. Graph to find intersection. All right, you can always, I would use that as your last resort. I know some of you feel like doing that first, but you realize you might not always have a graphing calculator to help you do that, because you know sometimes we have non-calculator quizzes or tests. Maybe you have a calculator, but the directions say show your algebraic work. Okay, utilizing a calculator is not going to help you there either. So we got to get used to the algebraic steps of using those logs to cancel out exponentials. But if you do have a calculator, maybe you want to graph it to check your work. All right, so let's check out just some of these examples, getting used to using these logs. Can we get the exponential part all by itself? First of all, what is the exponential part? Can we identify it? What's the base to the power? What do you think, Kyle?
E to the power of 2x plus 1.
All right, that is your exponential piece, just a base to a power. Anything else on that side of the equation needs to be moved to the other side. So that 3 out front, let's go ahead and divide it over. All right, so we isolated the exponential. We got it all by itself. Now we want to try to convert it to a log. We're going to move the base of e to the other side of the equation. What kind of log do we need to use? Yeah, natural log. Okay, so when we move the e over, it becomes a natural log. The argument would be 4. And since we move the e over, we're just left with that 2x plus 1 power. All right, now before we get to calculator happy, we can keep solving for x by hand. We can subtract the 1 over. That would become the natural log of 4 minus 1, not the natural log of 3. Okay, you don't subtract the 4 and the 1 because the 4 is kind of trapped inside that argument section. And then we can divide the 2. So natural log of 4 minus 1 all over 2. There's your solution. No calculator necessary. Okay, we solved it by hand. But I know some of you might be decimal people. So if you have a calculator and you want to turn it into a decimal, you can. We'll go ahead and type in the natural log of 4. Make sure you close the parenthesis. And then minus 1. And we need to divide that by 2. So we get 1.93. All right, you can always check your work. You can take that decimal value, plug it back in for x, type the left-hand side into your calculator, and hopefully you get something close to 12. Do we want to try it or do we trust ourselves? You want to try it? Let's do it. We don't have to do all of them, but at least we'll get in the habit of maybe checking a few. So we need to type in 3 times e, and then in the power, we need 2 times 0.193, which was our x solution, and then plus 1 up in the power spot. As soon as we hit enter, hopefully it's something close to 12. I'd say so. All right, so you solved appropriately by hand. Let's try another one. Take a look at the right example. Can we identify the exponential part? Base to power, that'd be 2 to the 3 minus x. We want to get that all by itself. So let's subtract over the 4. All right, so now we want to convert it to a log. We're going to move the base of 2 to the other side. So what's that going to look like? Go ahead, Kyle.
2, sorry.
It's okay.
Log 2.
Yeah? Log base 2 of 6. Perfect. If If you move a base, it becomes a log, specifically with that same base number. So log base 2 of 6, and then we're left with 3 minus x on the left-hand side. Let's keep solving for x by hand. Okay, we'll not use we won't use a calculator till the end. So if we subtract over the 3, we'll have negative 3 plus log base 2 of 6. And then divide the negative, we'll get 3 minus log base 2 of 6. There's your x solution. No calculator needed. So this is what when you're taking a quiz or a test, perhaps on a non-calculator section, this is what some of your maybe answer choices would look like, okay, where they still have logs in them. However, if you have a calculator, maybe you want to type it in. We'll see what this is as a decimal. We need 3 minus log base 2 of 6, but we don't have a base 2 log button, so we're going to have to use that change of base property. We'll do log of 6 divided by log of 2. Looks like we get 0.415. Do we want to check our answer, or do we trust ourselves? You want to check it? Let's do it. Alright, so on our calculator, we'll go ahead and type in 2 to the power of 3 minus our x solution, which was 0.415. You're going to have to arrow over to bring the cursor back down, and then we'll go ahead and add 4. The moment we hit enter, hopefully it's something close to 10. And I'd say it is. Looks like we're good so far. Do you guys want to try the next one on your own? Give it a shot. Isolate the exponential part, move everything else over, use a log and see what you get. Were we able to do that fairly quickly? How about the natural log of 3 plus 1? Did anyone get it as a decimal? Good, Brooke? 0.098. Sounds good to me. Alright, you can check your work, plug it back in for x. The moment you hit enter, you should get something close to 10, just to be safe. Okay? Let's try the next one. So, at first glance, if we tried to approach this one the same way we did the other 3, we wanted to get the exponential part all by itself. But when you take a look at this problem, notice how we have 2 exponential pieces. We have an exponential on the left and an exponential on the right. So there's no way we can get one of them, okay, all by itself when we have 2 of them going on. So utilizing a log might not be necessary, at least for this one. How might you want to try this example? Yeah?
So you would make it 82 and then multiply x minus 1 by 3, so it would be 3x minus 3.
Perfect, okay? If we can get the bases to be the same, let's go ahead and do that, because I know most of us are familiar with that method from the last unit. So it is possible for us to get 8 to turn into a base of 2. Brooke said that would be 3. And then she also mentioned if you have a power to a power, you can multiply them together. So now that the bases match, we'll just check out the exponents. What's going to happen? Yeah?
The x's are going to cancel out.
Yeah, so you're essentially left with like -3 equals 4 or 0 equals 7, depending on how you solve it. What's that telling us? No solution. That is totally a false statement. So there is no possible number for x that you could plug in for the left-hand side to equal the right-hand side. Graphically speaking, there'd be no intersection point. Okay, you can check it out that way too, if you have a calculator. How are we doing so far? Pretty good? Okay, if you move an exponential base to the other side of an equation, it becomes a log base. Okay, inverses. Let's check out kind of a few trickier ones. We'll try these top two. All right, so on the left-hand side, we have e to the 2x minus 4e to the x minus 5 equals 0. If, again, we were to try to isolate the exponential part, notice how we have 2 of them. Okay, so we can't just get one all by itself. We also cannot get the same base on the left and the same base on the right because that little minus 5 in there is kind of screwing things up for us. Let me flip this paper for a moment. This last example we did. If I were to throw in, for example, a plus 3 on the end, do you think we still would have been able to solve it this way? No, right? Because we got the 2 to be, or the 8 to be a base of 2, the 2 to be a base of 2, but that plus 3 on the end, not quite going to work out for us. So this 5, there's no way we can get that to match a base of e. So what do you think we're going to try to do? If we can't get the bases to match, and we can't isolate an exponential to use a log, what could we try? We could graph it, okay? But I want to show you maybe a different way. What if I were to kind of jog your memory for a second? Instead of e to x's, what if I just use normal x's? Okay, I'll cover that up for a second. How would you want to solve that one? Factoring. How would it factor? Two numbers multiplied to -5.
Minus 5x plus 1.
Good. And if I asked you to solve for x, 5 and -1. Perfect. Okay. Let's see if we can do something similar here. Notice how it's basically the same setup, just instead of e, or instead of x's as your variables, we have e to an x as your variable. So we should technically be able to factor this one as well. Two numbers that multiply to -5 add to -4. We said we're -5 and +1. But instead of having x's as the variable, what do we have in this case? E to the x. Remember, e is just a number, it's not a variable. So you need e to the x, that way you have a variable in there. So how do you think we can solve for x in this case? It was pretty simple for us to figure out 5 and -1 when we did a normal polynomial or quadratic, but how do you want to go from here? How did you know 5 and -1 were the x solutions? What do you think, Kyle?
Set each factor equal to 0.
There you go. We can do e to the x minus 5 equals 0, and then we'll check e to the x plus 1 equals 0. Now we have two simpler equations to help us solve. Notice how we have one exponential piece in each of them. So in this first one, if we move the 5 over, we'll get the exponential part all by itself. And then if we want to move the e over, what's going to happen with that? Natural log of 5. Good. So there's one x solution. Maybe we'll see what that is as a decimal. Can someone type that in for us? Natural log of 5.
1.609.
Say it again.
1.609.
Thank you. All right. Let's go ahead and try the other one. So we'll subtract the 1. If we move a base of e to the other side, becomes a natural log. Why not? That's good. What's negative? The argument. Okay. No solution because the argument is negative. That's great, you guys remembered that. Okay. Just in case you wanted to double check, you could type it in on your calculator. Natural log of -1 pops up as an error message, meaning not possible. Okay. What if this was natural log of 0? Natural log of 0? Not quite. Another error message, right? Not possible. Check this out. Like if I had the natural log of 0, that's stating e to what power is 0. E to the first is e. E to the 0 power is 1. E to the -2 is 1 over e squared, right? There's no way you're going to get an answer of 0. So in addition to this concept that we talked about on Friday, how the argument cannot be negative, it also cannot be 0. So you're essentially just wanting a positive number in there. No 0, no negative. Those are going to kind of mess it up. Okay? So the only solution we would have to in this case is 1.609. So we'll write only solution. Good. Do we see that connection though with factoring? That's a pretty similar setup, just with e to the x's instead of x's. Works the same way. What about the next one? What are some of your ideas? Graph it. Okay, let's go through our checklist. Can we get the bases to be the same? No. Can we isolate one exponential part? No, because we have 2 of them. So of those 2 options, none of them work out. Let's go ahead and graph it. All right, so let's see. In y1, we'll type in 2 to the x plus 2 power. In y2, 5 to the x minus 3. Maybe we'll let our window be -10 to +10 in every direction, just as a starting point. And we'll hit graph. I don't think we can see the intersection point, right? Looks like they're going to cross somewhere way up here. So we got to go a little bit higher than 10. What do you guys want to go up to? 100? Okay. Let's change it to 100. Not quite. They're getting closer though. We still got to go a little higher. 150?
1,000.
Oh, still got to go higher than 150.
No,
500? 500? Okay. 499. All right, so it's somewhere right there. How do we find an intersection? Second calc, intersect, then what? Enter, enter, enter. Oh, perfect, right there. So 6.782. There we go. All right, so we'll go through our little checklist again. If you can get the bases to be the same, might not be a bad idea because we're familiar with that kind of method from the last unit. If the bases cannot be the same, maybe you can isolate the exponential part and then use a log to help you solve by moving the base to the other side. But unfortunately, if that is not an option, or if that's not an option, we'll go ahead and graph it when we have a graphing calculator to find the intersection point. How are we doing? Pretty good? All right, we're going to stop there for today. We're going to check out very similar questions, but this time they're going to be logs. So we might have to utilize exponentials to help us solve that whole inverse idea.